All right, thank you, Leah. I am Luca Mastropasqua, and I am a senior research scientist at the National Fuel Cell Research Center at the University of California, Irvine. And today I would like to offer you a perspective on using high temperature electrochemical systems to decarbonize some of the, what we call today, difficult to decarbonize sectors. And I'll give you some examples of these and how these work and can be integrated into these applications. So before we go into the actual topic of the seminar, I would like to introduce the National Fuel Cell Research Center at UC Irvine. The center was funded with funding from the California Energy Commission and the US Department of Energy at the end of the 90s to facilitate, demonstrate, and accelerate the deployment of fuel cell systems. Today, the concept of fuel cell technology and systems is broader. We work on any type of electrochemical systems. And then the second point of the mission of the center is to promote strategic alliances in relation to market integration of these systems. And some of these alliances are listed here. Again, we have the California Energy Commission, California Air Resources Board, the Air Quality Management District, the US Department of Energy, and others. And then in the private sector, we regularly work with companies like Fuel Cell Energy, Oriba, Toyota, Plug Power, and so on. I've also included a nice overview of the landscape that we see regularly next to our campus, and I have the luck to work next to. And also, luckily or unluckily, depends, we also have an anteater as a mascot for our university. So after this brief introduction, I would like to introduce these difficult to decarbonize sectors for which I think electrochemical systems can give a contribution for their decarbonization. So I would like to tickle your brain with applications such as steel production, maritime shipping and long-haul freight, petrochemicals and chemical production, data centers. These are, let's say, non-conventional applications for which fuel cell systems and electrochemical systems can still contribute in terms of energy efficiency and decarbonization and reduction of air criteria pollutants emissions. To give context in terms of the market in which we operate in terms of in the fuel cell sector, I'd like to give an example of the magnitude of and the growth of the fuel cell sector in the past few years. Last year, it was the year of the gigawatt for fuel cells. So there was more than 1 gigawatt installed in 2019, and as you can see, most of the installations were in the transportation sector, because and as I've shown in the previous slides, most of the conventional applications for fuel cells are related to cars and sometimes buses. So these applications use low temperature fuel cells like polymer electrolyte membrane fuel cells. What I'm going to focus mainly on today are these type of fuel cells that are not as much used, such as solid oxide fuel cells and molten carbonate fuel cells, as they are the high temperature ones and the one that we think are the best fit for integration into the industrial sector. So before we begin, I would like to give an introduction of the fundamental, especially of high temperature and solid oxide electrochemical cells. So when I introduce these systems, usually I like to divide them into 3 categories or 3 operating conditions. The first one here on the left-hand side is the galvanic mode, where the system operates effectively as a fuel cell. So we have oxidation at the anode of a certain type of fuel. That could be hydrogen, it could be an hydrocarbon, it could be a biofuel, a biogas, and then a reduction that occurs at the cathode. And the electrolyte works as an oxygen ion transport medium, while electrons are transferred in an external electric circuit. And the reaction is spontaneous, and there is a conversion, a direct electrochemical conversion between chemical energy into electric energy and heat. On the other end of the spectrum, we have electrolytic cells, where that effectively operates in an opposite fashion to galvanic cells, where we have a non-spontaneous reaction, where we have the direct conversion of electric energy and heat into chemical energy. In the middle, I usually report what I call short-circuited cells, which are effectively membranes, oxygen separation membranes in this case. And we've tried to include, integrate these type of systems also for oxygen production in oxy-fuel combustion systems, for example. The driving force of all these systems, all these electrochemical cells that I'm going to talk about, is really a gradient in electrochemical potential. Because when we supply fuel to the anode and an oxidant stream to the cathode, we offer a chemical gradient potential, a chemical potential gradient in the electrochemical cell. And then because we have a charge transport both inside the electrolyte and in the external electric circuit, we have an electrochemical potential gradient. So a combination of the chemical potential and the galvanic potential. So I've qualitatively sketched the gradient of the ionic potential gradient in a typical fuel cell condition, where we have the ionic potential that is greater at the cathode side and lower at the anode side. And this creates a flux of oxygen ions from the cathode to the anode. And in order to maintain the charge neutrality of the system, we must have an equal amount of electrons flowing in the opposite direction. And this is where the electrons flow into the external electric circuit and produce useful work. And we've done this exercise to plot quantitatively this electrochemical potential gradient in a solid oxide fuel cell fed with natural gas in a planar geometry. And so you see a 3D chart for the ionic potential reported on this axis for the electrolyte thickness and across a channel for a planar fuel cell. Finally, for the sort of broad context, I would just like to summarize the main reactions that occur in a solid oxide fuel cell on the left-hand side and a molten carbonate fuel cell on the right-hand side. So a solid oxide cell, as I mentioned, uses a solid oxide electrolyte that conducts oxygen ions. And the oxygen ions go from the cathode to the anode, where we have the oxidation of the fuel. Operating temperature range is between 600 and 850 C. And this is why we think it's a good fit for many industrial processes. Similarly, the molten carbonate cells are unique in their operating condition because they transfer carbonate ions from the cathode to the anode. The electrolyte is a molten salt that conducts these type of ions, and these effectively operate as CO2 pumps. These type of fuel cells have been greatly explored for carbon capture and storage application, and I'll show some of the results that we've had also in this presentation. As a common feature for both of these cells, we have steam methane reforming reactions and water gas shift reactions that occur at the anode of both of these fuel cells, because the anodes material are nickel based, and both of these reactions are catalyzed by this element. So this is the reason why both of these fuel cells are very fuel flexible, and many different types of hydrocarbons can be used to power these systems. So now I would like to really go into the presentation topic, which is I've structured using these macro areas that we work at the NFCRC at UC Irvine. So I'll just touch upon some of these topics, and then I'll delve into more detail, especially in the final applications, which I think it's of interest to this audience. So the material development that we do at UC Irvine is mainly related to solid oxide fuel cell and electrolysis cells. At the moment, we are interested in studying the thermomechanical properties of glass ceramics for sealing a seal material in planar solid oxide cells. We are interested in understanding how these seal change their glass transition temperature, for example, or other thermomechanical properties during manufacturing and during extremely dynamic operation. Another example of topic of interest is related to the material selection for solid oxide electrolysis cells, especially in the fuel electrode, due to the degradation mechanisms that occur due to the high steam content in these in the fuel electrode. And at the moment, the latest testing, and that I would like to go into more detail, is the testing of new current collectors for fuel cells in order to improve the gas diffusion towards the active sites on the electrode, and improve or reduce the ohmic losses in the fuel cell itself. So this is an example of, or some of the pictures of the fuel cell that we are testing. So this is the view of the fuel cell in the cathode and anode side, and this is the current collector that we are testing. It's a nickel mesh, really porous, 98%, and you can see the porous sizes here. And again, we have this setup where we mainly test the solid oxide cells with and without these new current collectors. These are contracts from companies that are interested in developing, especially the microstructure morphology of these materials. So we test these cells using conventional electrochemical measurements like EIS and polarization curves. Sorry about this. So the second topic that I would like to touch upon is the cell development and testing. So here I'm talking about bigger cell or bigger stacks that we like to measure the performance of, and find ways to integrate cells into bigger systems. So we are at the moment really focused on the development of solid oxide electrolysis systems, and in particular the cell management and heat injection from higher temperature sources. So solid oxide electrolysis systems, as I briefly mentioned at the beginning, are systems that can produce renewable fuels or low carbon fuels using external electricity. But the real feature of high temperature electrolysis systems is that they can substitute at least part of the electricity that is needed, as reported here in this left-hand side chart, with some heat. So at higher temperature, we can substitute some of the Gibbs free energy, which is electric energy, basically, for the conversion for the conversion from electric energy to chemical energy with some heat. And so this brings about the possible integration strategies with high temperature heat sources. Also, another challenge associated to having external heat exchanged to and from the fuel cell is that, depending on the type, the operating condition of the actual cell, the cell can operate in an endothermic or an exothermic fashion. This brings about challenges, especially in terms of controlling the cell and heat management of the cell and the stack. So in this sort of topic area, I would like to go into the detail of the dynamics associated to exchanging heat in the cell and in the or to or from the stack, and then how we can control these systems when operated dynamically. So this is a test stand that we are using to test these type of solid oxide electrolysis and fuel cell systems. This is a Shore stack that we are currently testing. It's a 6-cell solid oxide Shore stack. The test stand can have the following capabilities. It can inject multiple fuels to the cell, so from hydrogen to hydrocarbons, or gasified coal, and so on. Because it has a fuel pre-processing section, such as a pre-reforming reactor upstream the actual stack. And then we can do reversible operations, so switching between fuel cell and electrolysis mode. And then we can we have the possibility of doing online electrochemical impedance spectroscopy measurements for testing the degradation while we operate the system, and also online GC tests. So the first thing that we usually do is to characterize the cell or the stack. And we perform characterization of these cells using chronopotentiometry and electrochemical impedance spectroscopy at different conditions. So on the left-hand side, we have, I've reported the polarization curves at different furnace temperatures. And on the right-hand side, we change the gas composition of the stream that we supply at the fuel electrode. So we first characterize the system, and we support all these experimental data with modeling activity. You can see how we usually calibrate the model on one of these polarization curves, and then we perform a validation trying to understand if the model can predict the other two curves. At this point, I would like to also try to answer two main questions. How would these systems operate when we couple them with renewable energy sources, such as solar PV and wind? If we want to produce renewable hydrogen or renewable fuels with these systems, these has to be able to operate dynamically without losing performance with time, and have a long lifetime in order to have a long or commercial interest, let's say. So what is the expected lifetime and degradation rates when we couple these systems to renewable energy sources? So to answer the first question, we have we have exercised the system with typical load profiles of solar and wind wind energy output. So on the left-hand side here, we have the current density input to the cell that represents a typical daily profile of coming from a solar PV plant during a sunny day. And on the right-hand side, you see the response of the system. So I mentioned that it's a 6-cell shore stack. So you can see 6 voltage responses. And you can see that the response of the system is in line or fast enough to follow the current input. This, of course, is a laboratory test stand. It doesn't have a complicated control system or doesn't have a complicated balance of plant. But the main thing is that the temperatures of the stack are maintained constant. In this case, for us, it's simple because we have an electric furnace that maintains the temperature of the stack. But I think the main conclusion here is that for commercial systems, we must design control systems that are able to maintain the temperatures in the stack at constant levels or fairly constant levels in order for the system to operate dynamically and follow the dynamics typical of renewable energy systems. A similar answer we find when we couple the system with wind profiles. So on the left-hand side, again, we have the input coming from a wind farm or a wind turbine in terms of current density. And on the right-hand side, we have the response of the stack. And once again, we have the response is fairly quick, and so we can assume that this stack is able to produce, let's say, hydrogen doing steam electrolysis, following the highly dynamic profile of a wind turbine. But once again, we have the temperatures inside the stack that are very well controlled. So the second question that we have is how much these systems would degrade in a long term if we keep on operating them dynamically, like in this example. So in order to answer this question, we did accelerator stress tests on some parameters on the stack, so durability tests. In this chart here, I reported a series of cycles, thermal cycles to the stack, where we operated the stack varying the temperature of the furnace between 700 and 800 degrees C at a ramp rate of 100 degrees C per hour. And we performed 30 cycles. We didn't perform many. We didn't want to kill the stack right away. But the main idea was to understand whether this type of operating condition, varying the temperature of the stack, would degrade the voltage performance. So I've focused on one of the cycles, and here, so on the left-hand side, you see the variation of the temperatures inside the stack. The blue line is the furnace temperature that we were able to that we control. All the other temperatures are measurements, thermocouples inside the stack. And you can see on the right-hand side the response of voltage performance of the 6 cells. So you can see the voltage dynamics is quite fluctuating, let's say. And also another interesting thing that highlights the complication in terms of heat management of these systems is that the dashed line here is the limit between the endothermic region below the dashed line and the exothermic region above the dashed line. So you can see that, for example, in this there are some cells that operate endothermically, and in this case, one cell that operates exothermically. So the challenge in a real system would then be to design again a really good control system that maintains the temperatures in the stack controlled. The result of the acceleration stress tests where that we could actually see the difference between the first and the 30th cycle in terms of voltage of the 6 cells. So this is the voltage difference in terms of in millivolts, and on the right hand side in percentage. So you can see that the average is around 0.5% of voltage loss after 30 cycles of thermal fluctuation. So, okay, we have, I think, a good indication that these systems can be coupled with renewable energy systems and can follow a dynamic operation in electrolysis mode with the conditions that we must design a control system that can supply the reactants at the correct rate and that can maintain the temperatures of the stack at reasonable temperatures, constant temperatures, lest having high degradation rates in the cells. So now I would like to move forward to the actual applications. In the National Fuel Cell Research Center, we call these killer app for hydrogen and for low carbon fuels. Killer apps are all the difficult to decarbonize applications, such as steel, such as chemicals and petrochemical productions, maritime shipping, data centers, trains, and so on, cement. Because we think that hydrogen and low carbon fuels produced via electrochemical processes can be really a common denominator to decarbonize these sectors. So I'm gonna really touch upon three applications for which we've done some work using these systems, which are maritime shipping, petrochemicals and petro refineries, decarbonization, and aviation. And I'll just briefly mention some of the application of these technologies. And then I'll delve into more detail two applications, data center and steel production, as these are applications of which I'm particularly excited about. So the first one is maritime shipping. So freight and heavy duty transport are applications that are very difficult to avoid and are also difficult to decarbonize using conventional electric batteries methods. So here we suggest to use low or zero carbon fuels as an alternative. We have shown in the past, and many other in the literature have shown, that hydrogen can be used to decarbonize heavy and medium and heavy duty trucks and transport. We have demonstrated that we can use solid oxide fuel cells coupled with gas turbine systems to power long-haul locomotives. And also fuel cell-based marine vessels. So the question that we wanted to answer for this exercise was, can the ports of Los Angeles and Long Beach, which are the biggest ports on the Pacific coast in the US and one of the biggest in the world, can they become zero emission? So the large scale system-wide transition of these ports to net zero entailed challenges that haven't been explored before. So here we propose the transition to hydrogen of all the interstate, intrastate, and international freight transport that originates in California and cannot be already electrified using battery methods. So basically here we electrify everything that we can using battery methods, and everything that we cannot electrify using battery methods, we transition to hydrogen. So here I'm including long distance trucking, rail, ocean-going shipping, and so land-based and marine-based operation of the ports. So we find that that we need from 9 to 10 million tons of hydrogen per year to decarbonize all these loads in Los Angeles and Long Beach ports. But to our surprise, also, we also found that we can produce this much hydrogen using three quite big, but three wind farms in the northern coast of California. So, so how do we, if we produce this amount of hydrogen here, we need to transport it, we need to store it, we need to liquefy it, and we have to dispense it to the actual loads in the ports down here. So we try to design all the pipelines and the storage systems that has to be built to move this amount of hydrogen per year from the northern coast of California down to Los Angeles and Long Beach. And then we also try to answer the question, how much would that cost? So with a scenario of out to 2050, considering that renewables will decrease their cost and the electrolyzer technology will decrease their costs, we performed our techno-economic analysis and we came up with some numbers for the different technologies of electrolyzers. So solid oxide cells here, polymer electrolyte membrane cells here, and alkaline electrolyzer here. And in all conditions, using wind and solar, we can reasonably say that we will be able to supply renewable hydrogen at around $2–3 a kilogram. This including production, transportation, storage, liquefaction, and dispensing to the final loads. Then I would like to move on to the second example of killer app, which is aviation. In this case, we are developing new powertrains for all-electric aircrafts. These powertrains are based on solid oxide cells, especially low-temperature metal-supported solid oxide cells, to allow for faster transition and to have a higher power density. And these powertrains will be supplied with liquid biofuels. The main goal is to achieve energy densities that are close to what we have today for jet fuels and jet engines. The third type of application is the decarbonization of petrol refineries or petrochemicals production. For this study, we focused mainly on the one type of emission source in refineries, which is the steam methane reformer. The steam methane reformer is the main producer of hydrogen in a typical refinery, and it's one of the biggest emission sources, CO2 and criteria air pollutants emission in a typical refinery. So what we did was to design a solid oxide fuel cell system that would produce, at the same time, using natural gas, would produce electricity, would produce hydrogen, and would produce a processed steam. So it's a tri-generation solid oxide cell that can produce the same quantity of hydrogen of a typical steam methane reformer plant in a refinery, but on top of that would be able to produce electricity and steam. So we did all our mass and energy balances of the integration of this system that I'm not going to go into the details of here, but you can find more detail in this reference. But we also assess the air quality impact of transitioning all California refineries to using electrochemical systems instead of the conventional ways of producing hydrogen. And so this was, of course, a modeling exercise where we imagine to replace the power plants and the steam methane reformer plant in the California refineries. And you can see here the effects in terms of ozone reduction and particulate matter reduction. Here is where I am at the moment, where we have a lot of refineries next to highly populated areas, and the effect in terms of air quality and health benefits of many extremely populated areas can be enormous. So now I would like to again move forward and go into more details of two main applications: data centers and steel production. So in the virtual life that we are living now, everyone can understand that data centers and digital services, internet traffic, are all applications that are increasing their energy consumption, and with all probability, it will keep on increasing in the future. Also, it's a very demanding or challenging application, because the producing power for this type of application requires constraints such as extremely high reliability, like 99% uptime. So trying to find a new power generation paradigm for this sector is really challenging. So what we are proposing is to use hydrogen or use low carbon fuels to decarbonize data centers. We have tried both low temperature fuel cells and high temperature fuel cells as a direct integration with server racks. We have a long-standing relationship with Microsoft, and so it's since 7 years we have tested different types of cells coupled with their server racks. One of the challenges that Microsoft pointed out about using low temperature polymer electrolyte membrane fuel cells is that they require hydrogen. And today, we don't have a widespread hydrogen infrastructure yet. So they were interested in having the same type of solution by using solid oxide fuel cells instead, that can use natural gas as a fuel, and then for now, and then in the future, they can be transitioned to either a synthetic renewable natural gas or renewable hydrogen. So what we first did was to test solid oxide cells coupled with server racks. And this is an example of the test stand that we put together using a 2.5 kilowatt electric commercial solid oxide fuel cell with a direct DC coupling to a server rack. So we removed all the power electronics from the fuel cell, and we directly coupled this the output of the two stacks that make up of this system to the DC input of the servers. As always, we characterize the stacks first of all. So we here I've reported an example of the polarization curve for the two stacks, stack 1 and stack 2 in blue and red, for this commercial system. So as I mentioned, we must make sure that these systems can operate dynamically. So we used a dynamic profile supplied by Microsoft and exercised the system for 1,000 cycles, each cycle 1 hour, and verified that the system could actually follow the load profile and then calculated the degradation, if any, of the two stacks. And actually, we couldn't see, or we couldn't measure any real degradation after 1,000 cycles. Between the first and the 1,000 cycles, the system was performing fairly well. So this was a good news, promising news for these systems to again be exercised dynamically, such as in this case. The second demonstration that we are doing in relation to data centers is for producing both electricity and heat or cooling for the server racks. So in this case, we have 8 solid oxide systems placed up here that are directly coupled to the server rack that you see in the center of the picture, and so supply electricity to the server rack. But also we collect all the exhaust lines from these high temperature fuel cells, and we supply the exhaust lines to an absorption chiller that is placed behind here to provide cooling loads to the server rack. So in this case, again, when we will operate these systems with pure hydrogen, we will be able to provide both electricity and cooling to the server rack using renewable energy. So we have 8 systems, 1.5 kilowatt each, 15 kilowatt thermal of absorption chiller, and really the purpose is to operate these systems dynamically at different operating conditions. We are testing the cell in order to produce exhaust lines at different temperatures in the range between 100 and 300 C in order to exercise the absorption chiller in different conditions. Also in this case, we have characterized the solid oxide cells first, like using a polarization curve such as the one that I've reported here. In this case, I just want you to notice the time that we need to allow for this for performing a polarization curve. This is a 1-day cycle basically, because of the thermal in order to reach thermal stability or a steady state in the two stacks. The thermal inertia of these stack is quite big, so we need to allow sufficient time to reach the thermal steady state of the system. And even here, we still see an hysteresis between the forward and backward branch of the polarization curve because of this thermal inertia of the stacks. We performed long power cycles of these systems in order again to understand the degradation rates. And after a month of operation using that type of power cycles, you can see the difference in voltage between the first and the last day. Also in this case, the voltage difference is noticeable, but it's doable in a commercial system. And also in long-term operation, we've tested these systems for almost 4 years now, and exercising it with hydrogen injection in the natural gas line and at partial loads. And so you can see the long-term operation and the voltage dynamics in this is about 1 year of operation in our lab. Okay, so now that we've discussed data centers, I would like to move to the last topic that it's quite of interest to me. We have just won a US Department of Energy award for integrating solid oxide electrolysis cells into direct reduction iron plants for production of renewable steel. And this is, I think it's a very interesting project. We have this consortium of companies and universities. We are collaborating with Fuel Cell Energy that provides the electrolysis system, Hatch that will help us with the scale-up design. LEAP and Politecnico are two Italian partners that will perform the thermodynamic analysis and system integration, and then SoCalGas as a co-sponsor of the project. So the idea here is that nowadays most of the steel production is made using blast furnace and basic oxygen furnace route that uses coal both as a main reactant and also as a mechanical structure of the actual furnace. So it's quite difficult to replace coal if we are using conventional steel making routes, for the reason that it doesn't just provides the reactants, but also provides the sort of mechanical integrity of the furnace. So we have two strategies mainly to reduce the CO2 emissions from steel making. The first one is using carbon capture and storage, and we have applied this strategy in this paper here that's just published, using molten carbonate cells as retrofits to steel plants. But the route that we have proposed in this project is using an alternative steelmaking route, which is direct reduction iron. So here, the main idea is to use reducing gas, such as hydrogen or carbon monoxide or syngas, to reduce iron ore, which is mainly iron oxides that are fed at the top of this counterflow furnace. So iron ore is fed from the top, and this reducing gas is fed from this side. And the counterflow configuration allows to perform a reduction of the iron ore and produce iron at the bottom of the furnace. And then the reducing gas reacts, and at the top of the furnace we have water and CO2. So the system that we have proposed is uses a solid oxide electrolysis system to produce the reducing gas for the DRI furnace. So we have production of hydrogen at the outlet of the cathode of the SOEC, and the hydrogen, after some preheating, is fed directly to the shaft furnace, where reacts with the iron ore. At the top of the furnace, we have only steam exiting effectively because we don't have any more carbon in the loop. And the steam that it's produced at the top of the shaft furnace is then looped back into the cathode of the SOEC. And as a note, we also produce at the same time pure oxygen that can be used for oxy-fuel combustion, like in this example for preheating, and also to export. So the idea of the project is to demonstrate this concept using a harder-in-the-loop configuration. So we will have a real system, a prototype produced by Fuel Cell Energy that will be coupled to a DRI simulator, real-time simulator that will simulate the functioning of the DRI, the shaft furnace. So the prototype will produce reducing gas that will go and will be processed by a series of physical actuator and software to simulate the operating of the shaft furnace. And then the software will then tell the actuators basically what type of gas the shaft furnace would produce, and that gas will be produced and sent back to the SOEC system. So this project will start in January next year. So and will last for 3 years. So stay tuned, because we are quite excited to start. I think I got to the end. I would like to conclude with conclusion slides and possible sort of view for future ideas. I've talked about some of the difficult to decarbonize applications, but there are many other applications that I haven't mentioned, and many sectors that we still need technology to decarbonize them. So we should use all of these techniques: carbon reduction using CCS, carbon removal using direct air capture systems, to reduce the CO2 emissions from all these difficult to decarbonize sectors. And then my final suggestion or idea is that there are countries that already are investing so much in oversizing their grid capacity with renewable energy that have become so cheap, exactly to use all the carbon produced using all these methods and produce valuable commodities and high value products. So the conversion between CO2 and a valuable commodity using electrons, I suggest will have to pass through one of these electrochemical processes. And these valuable commodities could be carbon-based, such as ethylene, such as either hydrocarbon chains, or we could use these electrochemical processes to do the polymerization of plastics, or, as reported here, nitrogen-based chemicals such as ammonia, that will be very important for the maritime sector, or it's been considered by many industries in the maritime sector. And then there is the whole word about smelting of metals, such as production of iron or other metals. So with this, I would like to conclude and thank all my collaborators, the faculty members, and the researchers at the NFCRC, and all the PhD students that I work with. And I'm happy to take any question.